Fisher. I'm in the class of 2014, and today I would like to talk to you about quantum mechanics. So when I first started learning about quantum mechanics at the beginning of this year, I would tell my friends, I would try to explain to my friends what I've been doing with my time, and I don't think they entirely understood what I was really learning. So basically, quantum mechanics is the branch of physics that explores the behavior of subatomic particles. Before I could really delve into quantum mechanics, I first had to learn some basic math behind the science. I learned trigonometry, complex numbers, linear algebra, and how to compute eigenvectors and eigenvalues. I started my study by looking into wave functions. Wave functions are equations used to describe the movement of particles. Pictured here are two common wave functions. The arrows basically indicate the probability amplitudes that a particle will be in a certain state at a time. Inside these wave functions you can calculate position, velocity, momentum, all from these equations. I then looked into quantum computing operations. These matrices, when multiplied by states, will change the values of the probability amplitudes. From these operations, you can calculate eigenvectors and eigenvalues. Here is one calculation for the eigenvalues of the bit flip. The eigenvalues are basically numbers that, when multiplied by a state, are equivalent to the computing operation multiplied by the state. Here is how you compute eigenvectors. Eigenvectors are basically states for which the eigenvalues hold true. So here is one computation for finding the eigenvectors of operation. Here's a neat little trick that I thought was really cool that shows how the original operation is embedded within the vectors and values. So if you take a matrix of the eigenvectors and then multiply it by a diagonal matrix made up of the eigenvalues, and then multiply it again by a matrix made up of the eigenvectors, then the result is the original operation. So that just shows how the operation is within the values and vectors. So after I learned these basic quantum mechanics skills, I delved into the classical quantum mechanical problem, particle in a box. Particle in a box takes a stationary system, a box, and tries to predict where a particle will be in the box. So to do this equation, you need Schrodinger's equation, which is the equation for motion in quantum mechanics, pictured here. The first section of numbers calculates the potential energy of the electron, and then the V calculates the kinetic energy of the electron. I wrote a program that would calculate do the Schrodinger equation for a hydrogen electron and then graph it. So the dots here are the eigenvectors, each number in an eigenvector. And as I move my mouse up and down, I change the eigenvalue associated with that eigenvector. And that's how you predict where a particle will be in a box at a time. And as you can see, the dots travel in waves. So while all of this may seem like theoretical mumbo-jumbo, it actually has a lot of direct applications in our life today. For instance, right now, a brand new technology are quantum computers, which basically, rather than calculating usually using binary code, they calculate using atoms and molecules and subatomic particles. And by doing this, they are able to do calculations much faster. So they can do things like predict which way a protein will fold, or test space aircrafts, and loop through the human genome. A lot of things that were impossible before just because they're so time-consuming. But with these new quantum computers, they're made possible. So I hope today you've come to understand a little more about what quantum mechanics actually is, and realize that it's not just this theoretical thing that has no practical applications. So thank you.